Hello my dear children, welcome back to my channel. This is Vidya Prabhu here, your maths teacher. Chapter number 1, Real Numbers, Theorem 1.2. Let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. Let me explain this theorem by using an example. It is given that we have a prime number P. If a prime number P divides A square, then P also divides A. So I am going to consider an example. Let 3 be a prime number if 3 divides a square number 36. We know that 3 is a prime number and 36 is a square number. 6 are 36. If 3 divides 36, it is obvious that 3 divides 6. Correct? If a given number is a square, that is 6 are 36. What is a? A is nothing but the number 6. The square root of 36 will be 6. If any prime number divides a square number, it also divides the root of the given number. If any prime number divides a square number, it also divides the root. Let me consider one more example. If 5 divides a square number 25, then 5 can also divide 5. Why? Because 25 can be expressed as 5 into 5, right? So if any prime number divides a square, it also divides a. If we have let P be a prime number, if P divides a square, then P also can divide C. If any prime number divides a square number, it also divides the square root of that particular number. If 5 divides 25, then a prime number 5 can also divide 5. That is theorem 1.2. The next theorem number 1.3, we need to prove that root 2 is irrational. We are going to prove this theorem by the method of contradiction. So, let us assume to the contrary that root 2 is rational. So, we can find co-prime integers a comma b, where b not equal to 0. Root 2 can be expressed as a by b. We know that we have assumed that root 2 as a rational number. We have learned the definition about rational number. Any rational number can be expressed as numerator by denominator. Denominator should not be equal to 0. So we have assumed root 2 equal to a by b. Just cross multiplying. Root 2 into b is equal to a. Squaring on both sides. Root 2 b the whole square is equal to a square. Root 2, when you take square and square will get cancelled. So 2b square is equal to a square. Now we are going to apply the previous theorem, that is nothing but 1.2. The 1.2 theorem states that let P be a prime number. If P divides a square, then P also divides a, where a is any positive integer. So by theorem number 1.2, we come to know that 2 divides a square, then 2 also divides a. If 2 divides a must be a multiple of 2. So, we can write a equal to 2 times of c for some integer. Let this be equation number 2, and you can take 2b square equal to a square as equation number 1. Substituting 2 in 1, b square is equal to, a can be expressed as 2c the whole square. So 2b square is equal to 4c square. Dividing by 2 on both the sides, b square equal to 2c square. Now again by theorem 1.2, 2 divides b square, which implies 2 also divides b. So we can come to the conclusion that a and b have 2 as a common factor. Therefore, we can find a and b have at least 2 as a common factor. But this is contradiction to the fact that we have assumed that a and b are co-prime integers. What is the meaning of co-prime integers? The HCF of a comma b is equal to 1, which means that a and b have a highest common factor of 1. Since we have assumed it as a co-prime integer, we arrive a contradiction that a and b have at least 2 as a common factor. This contradiction arises because we have assumed that root 2 is rational is wrong. Therefore, we can conclude that root 2 is an irrational number. We can find that a and b have at least 2 as a common factor, but this is contradiction. This is contradiction to the fact that a and b are co-prime integers. Therefore, our assumption is wrong. That is, root 2 is rational. We have assumed that root 2 as a rational. So our assumption is wrong. We can conclude that root 2 is irrational. Thank you for watching my video.